Alrighty, in this video we are looking at sequences and series. More specifically, this is just an introduction to sequences. This is our first lesson from chapter 12. So let's get started. Our objectives are to find any term of a sequence, given its explicit or recursive formula, and to use pattern recognition to write an explicit or recursive formula for a given sequence. This is what I aim to teach you through this video. So let's get started. I need to begin by defining what a sequence is. It is a function whose domain, that's the input, that's the x values, is the set of positive integers. So the domain could be numbers like 1, 2, 3, 4, 5, 6, so on and so forth. That is what a sequence is. And in a sequence, each number in that sequence is called a term. So the outputs, so if you're like at position 1, the output, the value of that number or whatever you're working with in the sequence is called a term. Now we have two types of sequences. They can be finite or infinite. What does that mean? Well, kind of intuitive here. Finite, limited number of terms, whereas infinite will never end. It will have an infinite number of terms. Excuse me, I'm sorry. An example of a finite sequence would be something like this: 600, 400, 200, 0. There are 1, 2, 3, 4 terms in this sequence. Contrast that with 1, 4, 9, 16, ... Those little ellipses mean that it is going on and on and on in that manner. It is never ending. It is an infinite sequence. Now, what was mentioned in our objectives are explicit and recursive formulas. Well, let's start with the first. An explicit formula, those are written in terms of n, where n is the position number of the term in your sequence. And what's great about explicit formulas is you can find any term really easily. Let me show you an example here. What would be the next term in this sequence? Well, let's break it down here. Let me show you a method I use. I like to line up the position and the output. So n is the position. So the first position's output is 1. The second position's output is 4. The third position's output is 9. The fourth position's output is 16. So can we guess what happens next? What's happening each time? 1 giving you 1, 2 giving you 4, 3 giving you 9, 4 giving you 16. It seems as though we're taking the position and squaring it, so the fifth position, it would make sense to be 25. Now, what would be the formula that represents this? It would look like you see here. AN, where I don't know what N is, it could be anything, it just represents the position of your term, is going to be N squared, where N is, again, the position of that number in the sequence. So A sub 5, N is 5, the position is 5. 5 squared, that gave us 25. That is an explicit formula. Let's look at this example together. We want to find the first, the second, and the 10th term in the sequence using this particular formula. Our formula is AN equals N squared plus 3N. Now this is pretty easy to do so. just plug in the position number. We're looking for the first, so that would be 1. 1 squared plus 3 times 1, that gives us 4. So A1 is 4. The first term is 4. The second term, I'll just plug in 2 for the position. A sub 2 is 2 squared plus 3 times 2, which gives you 10. And the last, we're looking for the 10th term, and we can do that real easily just by plugging in 10 into the position because it's in the 10th position. That's going to give you 130. So the first term, A sub 1, is 4. The second term, A sub 2, is 10. And the 10th term, A sub 10, is 130. It was really cool because we were able to skip from 2 to 10, and we could even just, if we wanted to, find the millionth term in this sequence just by plugging in. Here's another. Ooh, I like this one. Find the first, second, and 10th term in this sequence. The sequence is Bn equals 3. Well, if you plug in 1 for the n value, notice there is no n value, so it's just 3. And at 2, there's still just 3. And at 10, the output is still just 3. This is a sequence where nothing changes. It's just 3 for every position in the sequence. You can have sequences like this where every term is the same value. Inductive reasoning. You've probably seen this in your science classes. It's drawing a general conclusion from specific instances. So you look at these like case studies, and then you're able to kind of make an idea. You're inductively reasoning in this case. So let's look here and use that process to write an explicit formula. We're going to look at this specific case and kind of try and figure out what would be the formula that would represent any term in this sequence. To do so, again, I like to use that table. It really helps to kind of relate position and the output. So at position 1, it's 2/3. At 2, it's 4/5. At 3, it's 6/7. At 4, it's 8/9. So how is the output? How is each term related to its position? Let's look at the numerators first. Position 1, it was 2. Position 2, it was 4. Position 3, it was 6. Position 4, it was 8. It seems as though the numerator is just twice the position, twice your in value. And what about the denominator? 1 gave you 3. 2 gave you 5. 3 gave you 7. 4 gave you 9. Well, your denominator is just 1 more than your numerators. It's twice the position plus 1. So how do we write this out? Well, A sub n is 2n in your numerator, twice the position in your numerator, over 2n plus 1 in your denominator. And that, if you subbed in any value of n, any position, that would give you the correct term in the sequence. Kind of cool. Let's do another like it. Write an explicit formula for this particular sequence. Let's use our table, populate it. Okay, so what's happening here? The first thing I recognize, well, 1, output of 1, 2, output of 8, 3, output of 27, 4, output of 64. It seems as though the position is just raised to the 3rd power because 1 cubed is 1, 2 cubed is 8, 3 cubed is 27, 4 cubed is 64. But there's kind of a peculiar thing happening here. Notice it's negative, positive, negative, positive. There's a cool way to make that happen. To have in a sequence alternating signs like that, you just take -1 and raise it to the nth power. Because if you raise -1 to the 1 power, it's negative, which is what we wanted. To the 3rd power, it would be negative. But to your even powers, like 2 and 4, you get positive outputs. So your formula, your explicit formula, would be an equaling that alternating sign, that's -1 to the n, and then n cubed. All right, that's all I have for the explicit formula. Hang on tight and I'll get you more about the other type.